Hello everyone, today let's learn MPLS VPN basics. After completing this course, you will understand the principles and architecture of MPLS VPN, understand the basic concepts of the VPN instance, route distinguisher RD, route target RT, and multi-protocol extensions for BGP4, MPBGP. Understand the route exchange and data forwarding process of the MPLS VPN. This course consists of two parts. First, let's examine the basic concepts and principles of MPLS VPN. As the name suggests, MPLS VPN is a VPN based on the MPLS data plane. We are already familiar with the concept of MPLS, but what is a VPN? A VPN has two characteristics: virtual and dedicated. A dedicated virtual network is constructed over a public network to allow sites of the same VPN but in different regions to communicate. Now let's shift focus to BGP MPLS IP VPN, which is a type of Layer 3 VPN, L3 VPN. The name consists of four parts: BGP, MPLS, IP, and VPN, each of which represents a specific meaning. BGP advertises VPN routes on the backbone network of a service provider. MPLS forwards VPN packets on the backbone network. IP packets are transmitted on such a network. VPN indicates that BGP MPLS IP VPN is a VPN technology. BGP MPLS IP VPN supports overlapping address spaces, overlapping VPNs, flexible networking, and good scalability, in addition to MPLS quality of service, queues, and traffic engineering, TE. As such, BGP MPLS IP VPN is an important method for IP network carriers to provide value-added services and is widely used. Next, let's take a look at the BGP MPLS IP VPN network. Generally, this consists of the backbone network built by a service provider and a network built by a customer. The former is also called a public network, and the latter is a private network. Customers on different private networks share the backbone network, but are unable to exchange data with one another. The figure in the upper part shows that customers A and B each have two sites, and both purchase MPLS VPN services from the same service provider. The figure in the lower part shows a logical network from the perspective of customer A, who is unaware of customer B. An MPLS VPN involves the following roles. A CE is an edge device of a customer network, and therefore belongs to a customer. In addition to connecting to the customer network, the CE also directly connects to the MPLS VPN network through a specific interface. A CE can be a router, switch, or host. Generally, CEs are unaware of VPNs and do not need to support MPLS. A PE is an edge device on a service provider network and directly connects to a CE. VPN processing is performed on PEs on an MPLS network, and this poses high requirements on PE performance. PEs need to be aware of, obtain, and advertise customer network routes, which are also known as VPN routes. PEs are backbone devices on a service provider network and are not directly connected to CEs. PEs are only required to support basic MPLS forwarding capabilities and do not need to maintain VPN information or VPN routes. As different customers may use the same IP address space, for example, site 1 of customer A and site 1 of customer B use 172.16.1.0/24. PEs must be able to prevent route conflicts. Virtual routing and forwarding, VRF, is involved in this process. On Huawei Datacom products, VRF is also known as a VPN instance. VPN instances are used to logically divide a physical device, enabling multiple virtual devices, also called VRFs, to be created on the physical device, such as a router or a switch. Each virtual device works like an independent device. A VPN instance created on this device is equivalent to a virtual device, and a specific interface can be bound to it. In this way, the interface serves the VPN instance. Each VPN instance uses independent data forwarding tables, for example, a rating table. These VPN instances use different data forwarding planes so that traffic received on an interface bound to a VPN instance will not be forwarded to other such instances. VPN instances can be used to completely isolate services. On an MPLS VPN network, VPN instances enable a carrier to provide VPN access services for multiple customers on the same PE. The routes and data of these customers are isolated from each other, and conflicts do not occur even if these customers use the same IP address space. As shown in the figure, two VPN instances are created on the PE. VPN A serves customer A and is bound to interface 1, while VPN B serves customer B and is bound to interface 2. To allow customers to exchange VPN routes, a PE on an MPLS VPN network needs to advertise a route destined for the local customer side to the remote PE. MPLS VPN uses BGP to advertise VPN routes between PEs. However, traditional BGP cannot correctly process VPN routes with overlapping address spaces. Let's assume that customer A and customer B use IP addresses with the network prefix 1.1.1.0/24, and they both advertise a route destined for this network prefix. Although the local PE can distinguish VPN routes with overlapping address spaces through different VPN instances, it selects only one according to BGP route selection rules after they are sent to this peer PE. As load balancing is not performed among VPN-specific routes, as a result, the route to the other VPN is lost. To prevent VPN route conflicts caused by overlapping IP address spaces, route distinguishers RDs are used. Let's now take a look at how to use RDs. To solve address conflicts on the public network, the same VPN routes that are sent by different CEs and which may conflict with one another must be converted into unique public network routes. One method is to allocate an RD to each VPN instance. A VPN v4 route is composed of the RD and an original VPN route prefix. Since different RDs are assigned to VPNs, the VPN v4 routes become globally unique. To transmit these VPN v4 routes on the public network, BGP is extended to MPBGP. As shown in the figure, an MPBGP peer relationship is established between PE1 and PE2. MPBGP uses address families to differentiate network layer protocols. For the values of address families, see RFC 3232, titled Assigned Numbers. Regular address family views include the BGP view, BGP IPv4 unicast address family view, BGP VPN instance IPv4 address family view, BGP VPN v4 address family view, BGP IPv6 unicast address family view, BGP VPN instance IPv6 address family view, and BGP VPN v6 address family view. RDs are not used to distinguish which VPN instances VPN v4 routes are imported to. Instead, a route target, a 32-bit BGP extended community attribute, is used on an MPLS VPN network to control the advertisement and acceptance of VPN routes. An RT is also referred to as a VPN target on Huawei devices. When PE1 advertises the VPN route to PE2 using MPBGP, the route carries RTs. RTs are stored in the extended community attributes of BGP routes, and the VPN v4 route can carry one or more RTs. Each VPN instance is associated with one or more RTs, and two types of RTs exist. Export RT. A PE learns an IPv4 customer route from a directly connected site, converts it to a VPN v4 route, and then sets an RT for the route. The RT value is the same as the export RT value specified in the VRF, and this value is used as the extended community attribute of BGP, and is advertised to the remote PE along with the route. Import RT. When a PE receives the VPN v4 route advertised by another PE, it first checks the route's RT. If the RT matches the import RT of a VPN instance on the PE imports the route to the VPN instance. The setting of the export RT is independent from that of the import RT, and multiple values can be set for both the export RT and import RT to enable flexible VPN access control, thereby implementing various VPN networking solutions. For example, if the import RTs of a VPN instance are 100:1, 200:1, and 300:1, the received route can be injected to the VPN instance if its RT is either 100:1, 200:1, or 300:1. With RDs, MPBGP can transmit VPN v4 routes on the public network and select optimal routes based on BGP route selection rules. MPBGP uses RTs to determine the VPN instance to which VPN v4 routes are transmitted. PE2 removes the RD from the received VPN v4 route and advertises the route to the corresponding CE based on the RT. In this way, the CEs of customer A's side 2 and customer B's side 2 can learn the routes to their respective remote sites. Similarly, the CEs of customer A's side 1 and customer B's side 1 can learn the routes to their remote sites. Can CEs communicate with each other directly after the routes between them are reachable? The answer is no. This is because routes are exchanged between PEs across Ps, and the Ps on the public network do not maintain VPN customer routes. In the figure, IP packets will be discarded on the P if PE2 does not perform special processing on the IP packets received from the CE. MPLS tunnels are used to solve this problem. An MPLS tunnel is established between two PEs on the public network to ensure that IP packets of VPN instance are sent from one PE to the other PE through the P on the public network. The figure illustrates an MPLS LDP tunnel. However, there are two issues involved in the data forwarding process which must be addressed. 1. The local PE needs to determine the remote PE to which the IP packets of the VPN instance are sent. 2. The remote PE needs to determine which VPN instance the received IP packets are forwarded to. On an MPLS VPN network, two labels are used to implement these functions. 1. An MPLS LDP tunnel label is used as an outer label, ensuring end-to-end forwarding between PEs. The next hop in the route to the destination address can then be used to determine the tunnel for the packets received by the PE. In other words, the packets can be diverted to the corresponding tunnel based on the next hop. 2. A VPN label is used as an inner label and is assigned to a VPN route accepted by the local PE. The labels of different VPN instances have different values on the local PE, which records the mapping between the inner label and the VPN instance. The inner label is advertised when the local PE advertises the VPN v4 route to the remote PE. When the remote PE forwards a packet to the local PE, the packet carries the inner label, and this can be used by the local PE to determine the VPN instance to which the packet belongs. The inner label of packet remains unchanged when the packet is transmitted on the public network. Next, let's take a look at the route exchange and data forwarding processes of MPLS VPN. On a typical MPLS VPN network, a PE needs to learn the route to the directly connected customer site, and the CE must also learn the route to a remote site through a directly connected PE. A routing protocol between PEs and CEs is used to implement these functions. A routing protocol running between PEs and CEs can be OSPF, SS, or BGP, as well as static route. And you can flexibly select a routing protocol as needed for the PEs to exchange VPN routes. The PE-CE routing protocol running on the CE, such as OSPF, has no difference than a traditional protocol, while the PE-CE routing protocol running on the PE must be associated with a VPN instance. The routing protocol process needs to run within a VPN instance. For example, the OSPF multi-instance process is used within a VPN instance. PEs play the most important role on an MPLS VPN network and provide various functions. 1. Configure VPN instances to exchange routes with CEs and store VPN instance routes. 2. Establish IGP neighbor relationships on the public network and store IGP routing tables. 3. Establish MPLS tunnels and maintain all entries related to MPLS. 4. Establish MP-BGP peer relationships and maintain the VPN v4 routing tables. Before delving into the process of VPN v4 route advertisement on an MPLS VPN network, let's examine the regular configuration. 1. CEs and PEs maintain IGP neighbor relationships or BGP peer relationships and exchange VPN IPv4 routes. Regarding BGP, while eBGP is generally configured, static routes can also be used in some simple scenarios. 2. An MP-BGP peer relationship is established between PEs. If PEs are in the same AS, an MP-IBGP peer relationship is established to exchange VPN v4 routes and labels. This slide describes the route advertisement process. Step 1. Each CE advertises a private IPv4 route to PE1. Step 2. PE1 adds the VPN routes to the IP routing tables of the VPN instances. If an IGP or static route is used between the PEs and CEs, related IGP or static routes must be imported into the BGP process. Step 3. PE1 adds the RD to a VPN route prefix to form a VPN v4 route. In addition, the export RT is added to the VPN v4 route. Step 4. PE1 advertises the VPN v4 route to its peer through the MP-BGP peer relationship. Step 5. After receiving the VPN v4 route, PE2 matches the export RT of the VPN v4 route against the import RT of a VPN instance. If they match, PE2 removes the RD from the VPN v4 route and injects the IPv4 route to a specific VPN instance. Step 6. PE2 advertises the IPv4 route to a CE through a BGP peer relationship, and the CE adds the route to its own IP routing table. Now that we are familiar with the process used to advertise MPLS VPN routes, let's take a look at the data forwarding process. With an IGP and MPLS LDP configured on the public network, MPLS LDP tunnels are established. When PEs send VPN v4 routes to one another, the routes carry various attributes including the next hop, VPN label, and export RT. These VPN v4 routes are encapsulated in MP-BGP update messages. During data transmission, PE2 receives the data packet from the interface bound to the VPN instance. 1. PE2 adds a VPN label to the packet based on the VPN instance to which the interface belongs. 2. PE2 searches the routing table based on the destination address of the packet and finds that the next hop is PE1 1.1.1.9. The FAQ 1.1.1.9 is associated with an MPLS LSP, and the outgoing label for the LSP is 3111. PE2 then adds label 3111 to the packet. PE2 forwards the MPLS packet with double labels to P2, which then forwards the packet to P1 based on the outer label. P1 uses PHP to remove the outer label and forwards the packet to PE1. After the egress PE1 receives the packet with a single VPN label, PE1 determines a VPN instance based on the VPN label 1021, searches the IP routing table of the VPN instance, and forwards the packet to CE1. At that point, the MPLS VPN data forwarding process is complete. That's all for now regarding the basics of MPLS VPN. We hope you enjoyed this course, and thanks for watching.